On August 2, 1941, the concrete floor of the Packard Motor Car Company's East Grand Boulevard plant in Detroit trembled under a force it was never designed to hold. Inside the test cells, 2 Rolls-Royce Merlin engines roared to life, screaming at a pitch that usually signaled an imminent takeoff. But the men in suits watching through the safety glass were not looking at British engineering. They were looking at an industrial phantom. These engines, though they looked identical to the legendary power plants driving the Royal Air Force, were American-made copies. They were built from British blueprints that Packard's engineers had essentially shredded and rewritten from the ground up. The crowd watching that day had no idea they were witnessing a quiet revolution. Hidden inside those roaring aluminum blocks was a secret that would arguably do more to transform the trajectory of World War II than any single infantry battle. The bearings were chemically different. The tolerances were tighter than anything Detroit had ever attempted. Even the thread patterns on every single bolt had been painstakingly replicated from Britain's arcane and nearly obsolete Whitworth system. Detroit, the city of assembly lines and mass-market sedans, had just turned a hand-fitted, artisanal luxury engine into America's most mass-produced weapon of war, and they had done it by breaking every rule Rolls-Royce held sacred. To understand why this moment was so critical, you have to look at the skies over Europe in early 1942. The United States Army Air Forces possessed a fighter pilot's paradox. A plane they loved to fly, but a plane they could not fight with. The P-51 Mustang, powered by the domestic Allison V1710 engine, was an aerodynamic masterpiece. North American Aviation had designed a flawless airframe that was fast, agile, and deadly, as long as it stayed below 15,000 feet. But in the thin, freezing air above that altitude, the Mustang became a struggling, gasping liability. The problem was not the plane. The problem was physics. The Allison engine relied on a single-stage supercharger that simply could not compress enough of the thin upper atmosphere air to feed the engine's cylinders. By the time a P-51 climbed to 25,000 feet, the domain where German Messerschmitts and Focke-Wulfs prowled with impunity, the Mustang was down to barely 1,000 horsepower. It was an athlete running a marathon while breathing through a straw. By 30,000 feet, it was essentially helpless, wallowing in the air, an easy target for any enemy pilot who simply bothered to climb. This created a cruel and bloody irony for the American war effort. The doctrine of the U.S. Army Air Forces relied on B-17 flying fortresses to conduct daylight precision bombing runs deep into Kensi, Germany. These massive formations cruised between 25,000 and 30,000 feet to avoid anti-aircraft fire. But without escort fighters capable of matching that altitude performance, the bombers were essentially flying naked. They were being slaughtered. The Luftwaffe quickly realized the Allison Mustang's weakness. They simply climbed above the American fighters' service ceiling and dove on the bombers from above. During the catastrophic raid on Schweinfurt in August 1943, 60 bombers were destroyed in a single mission, a loss rate that was unsustainable. The Army did not need a new fighter. The airframe was perfect. They needed a transplant. They needed a new heart. 3,000 miles away in Derby, England, Rolls-Royce Limited possessed the solution the Americans were so desperately seeking. Their Merlin engine was already powering Spitfires and Hurricanes to altitudes the Allison V1710 could only dream about. The secret weapon nestled within the Merlin was a masterpiece of pneumatic engineering. A two-stage, two-speed supercharger system designed by the brilliant mathematician and engineer Stanley Hooker. Unlike the simple American design, Hooker's creation could maintain sea level pressure all the way up to 30,000 feet. It forced air into the cylinders with such violent efficiency that the engine never gasped, never choked. It was the perfect heart for a high-altitude fighter. However, the Merlin was not just a piece of machinery. It was the physical embodiment of a specific British philosophy. In 1940, Rolls-Royce did not build engines. They crafted them. Every single Merlin was essentially a hand-built prototype. The engine consisted of 14,000 individual parts, and the assembly floor in Derby looked less like a factory and more like a watchmaker's guild. In the British tradition, parts were not expected to fit perfectly straight off the machine. They were expected to be fitted. When a connecting rod did not quite match the crankshaft, a worker with decades of experience would take a hand file and shave off microns of metal until the fit was perfect. When bearing clearances varied, as they inevitably did, They were individually adjusted by skilled craftsmen who could feel the difference of a thousandth of an inch with their fingertips. The British standard Whitworth thread system, used on every bolt and screw, reinforced this bespoke nature. With its 55-degree angle and unique radiused corners, every fastener was a custom manufacture. This was a system born of the Victorian era, where standardization was secondary to individual excellence. The operating tolerances in the supercharger were staggering, measuring 0.0001 inches. To put that in perspective, that is the thickness of a human hair divided by 4. Cylinder heads were individually matched to engine blocks like suitors. Supercharger impellers were balanced by hand until they spun without a singular vibration. This process produced engines of exquisite quality, unrivaled in performance. This was art. But in a war of attrition, art has a fatal flaw: you cannot mass-produce it. By September 1940, with the Battle of Britain raging overhead and the Luftwaffe pounding London, the limits of this philosophy were breaking. Rolls-Royce's shadow factories in Crewe, Manchester and Glasgow were running their machines and men 24 hours a day, pushing the limits of human endurance. Yet, despite this Herculean effort, they were producing roughly 200 engines per week. The Royal Air Force needed 2,000. The math was terrifyingly simple. Britain was building the best engines in the world, but they were losing the war of numbers. Desperate, the British government looked across the Atlantic. They wondered if the sleeping giant of American industry could shoulder the burden. But what the British representatives did not fully grasp was that they were about to ask Detroit to perform an engineering miracle that seemed mathematically impossible. They were not just asking for factory space. They were asking American automakers to convert precision, handcrafted European artisanship into high-speed assembly line manufacturing without changing a single dimension, losing a single horsepower, or compromising a century of Rolls-Royce engineering tradition. They were asking for a translation between two industrial languages that had never been spoken together. The real challenge facing the Allied war effort was not just building engines. It was translating an entirely different industrial philosophy into the language of American mass production. When a delegation of Rolls-Royce engineers arrived in Detroit in September 1940, they brought with them crates containing complete Merlin engines, hundreds of rolls of blueprints, and an unwavering confidence in their methods. The licensing agreement they carried was worth $130 million, an astronomical sum for 1940, equivalent to billions today. Packard Motor Car Company was not the most obvious choice for this undertaking. Ford had already turned the contract down, citing political reasons and the difficulty of the task. Packard built luxury automobiles for America's elite, not high-performance aircraft engines for dogfights. But Packard possessed something Rolls-Royce did not: the raw, unadulterated power of American manufacturing genius. The moment Packard's engineering team cracked open the crates and examined the British blueprints, however, the air in the room shifted from optimism to dread. They realized immediately that they did not just have a difficult job. They had approximately 14,000 individual problems. The first problem was a nightmare of translation. The measurement systems were ostensibly the same. Both nations used inches and feet, but they were practically incompatible. Britain used imperial measurements, but their baseline standards were rooted in a pre-standardization engineering tradition. Rolls-Royce specified dimensions in thousandths of an inch, but these numbers were often nominal, serving as a starting point for the craftsman, rather than a hard limit for the machine. Converting these to American specifications was not simple math. It required deciphering the intent behind every single tolerance. The second problem was the British standard Whitworth BSW thread system. This was an archaic holdover that threatened to derail the entire project. Every bolt, every nut, and every threaded connection in the Merlin engine used a 55-degree angle thread form with unique radiused roots and crests. In contrast, the American unified fine thread system used a sharp 60-degree angle with flat roots. They were completely incompatible. You could not screw an American bolt into a British engine block. To build the Merlin, Packard would have to manufacture every single fastener in-house, using British specifications that did not exist in American tooling catalogues. But the third problem was the big one, the issue that made the Packard engineers sweat. Rolls-Royce's tolerances were designed specifically for hand-fitting. The blueprints were drawn with the expectation that a human being would intervene during assembly. Clearances of plus or minus several thousandths of an inch were common on the drawings, because the British system relied on the skill of the worker to make it fit on the bench. Detroit did not work that way. The American automotive production philosophy was built on the concept of perfect interchangeability. A piston manufactured on Monday had to fit into a cylinder block cast on Friday, regardless of which worker stood at the assembly line. There was no time for filing, no station for adjusting, and no reliance on a master craftsman to massage the parts together. American mass production required that the parts fit perfectly every single time, straight off the machine. The British engineers looked at the American assembly lines and were polite, but deeply skeptical. They believed that removing the human touch would ruin the engine. They asked, quite seriously, if American factories could really maintain Rolls-Royce standards without hand finishing. The tension in the conference room at Packard was thick enough to cut with a knife, or perhaps a hand file. The British delegation had laid out their case, implying that the blunt instrument of American mass production could never replicate the soul of a hand-built Rolls-Royce. They feared that without the intervention of skilled fitters, the engines would rattle themselves to pieces or seize up entirely. They waited for the Americans to admit defeat, to ask for concessions, or perhaps to request a team of British craftsmen to oversee the flaw. Instead, Packard's lead engineer, Colonel Jesse G. Vincent, leaned forward. Vincent was a legend in his own right, a man who had helped design the Liberty engine in World War I. He looked at the British blueprints, then at the skeptical faces across the table, and delivered a line that would become folklore in engineering circles. "Gentlemen," Vincent said calmly, "the problem is not that our factories can't hit your standards. The problem is that your tolerances are too loose for us." The room went silent. The British were baffled. Vincent explained that because Rolls-Royce relied on hand-fitting, their blueprint tolerances were actually quite wide. A part could be slightly oversized, because a worker would file it down. But in Detroit, oversized meant scrap, to achieve the perfect interchangeability required for the assembly line. Packard did not need to loosen the standards, they needed to tighten them. They needed to eliminate the variable of human error entirely. What followed was an engineering marathon. Over the next 11 months, Packard engineers did not just translate the blueprints, they reinvented the documentation of the engine. They created 6,000 new technical drawings. They were not correcting the British design, the geometry was sound, but they were redefining how that geometry was achieved. Every dimension was re-specified with rigid hard limits. Every manufacturing process was reimagined to be done by a machine, not a man. But the real genius of the Packard team revealed itself in the details, specifically in the metallurgy of the crankshaft bearings. This was a critical failure point for high-performance engines. Rolls-Royce used a copper-lead alloy for their bearings. It was a good material, but it was temperamental. It required a careful, lengthy break-in period, and frequent inspection, to ensure it was not galling the crankshaft. Packard's metallurgy team, drawing on recent American research into radial aircraft engines, proposed a radical substitution, a silver-lead alloy, plated with a thin layer of indium. The British engineers immediately objected. This was not in the specification, this was a deviation. But Packard insisted. The science was sound. Silver offered superior load-carrying capacity and fatigue resistance compared to copper. The indium, a soft rare metal, created a microscopically smooth surface that acted as a dry lubricant, drastically reducing friction and improving the embeddability, the ability of the bearing to absorb tiny grit particles without scoring the crankshaft. When the British finally allowed a test, the results were undeniable. The Packard bearings did not just work, they ran cooler, lasted longer, and required almost no break-in period. They were superior in every measurable metric. In a quiet admission of American ingenuity, Rolls-Royce eventually adopted the silver-lead indium composition for their own production lines back in Derby. It was the first sign that the student was beginning to teach the master. The thread problem, however, loomed like a logistical cliff edge. The easy solution would have been to simply re-tap the engine for American standard bolts. It would have saved months of work and millions of dollars. But Packard understood the grim reality of logistics in a global war. If a mechanic on a muddy airfield in East Anglia tried to repair a Detroit-built Merlin with a British wrench, and stripped the bolt, because the threads did not match. That plane was grounded. That pilot was out of the fight. The engines had to be 100% compatible with their British cousins. So Packard did something extraordinary. They did not try to change the engine. They changed the factory. They undertook the massive task of creating entirely new tooling to manufacture British standard Whitworth threads, but to American automotive precision standards. Every tap, every die, every thread-cutting tool had to be custom manufactured. Packard purchased specialized thread measuring equipment from Britain and set up training courses to teach American machinists a thread system most had never seen before. They mastered the BSW for coarse threads, the BSF British Standard Fine for precision connections, and even the Bayard British Association for small instrument fasteners. The result was a triumph of standardization. A Packard-built Merlin used exactly the same thread specifications as a Rolls-Royce engine, but with a critical difference. Packard manufactured those British threads to tighter tolerances than Rolls-Royce did. Every fastener came off the line precisely within specification. There was no hand fitting required. You could take a bolt from a Packard engine and screw it into a Rolls-Royce block made in Derby, and it would fit perfectly the first time, every time. Then came the supercharger, the mechanical heart responsible for the Merlin's high-altitude dominance. This two-stage, two-speed system was a beast of complexity. It used two impellers on the same shaft, driven through intricate gear trains. In low-speed mode, the drive ratio was 6.391:1. In high-speed mode, activated by a hydraulic clutch, it jumped to 8.095:1. These impellers spun at over 30,000 revolutions per minute. At those speeds, centrifugal forces are violent. The slightest imbalance of weight, even the weight of a postage stamp, would cause the assembly to disintegrate, destroying the engine in a shower of shrapnel. Rolls-Royce balanced these impellers by hand, with skilled workers adding or removing tiny amounts of material until the spin was true. Packard realized that this method was the bottleneck of Wallab production. Instead, they developed precision casting and machining techniques that produced impellers so consistently accurate, they required minimal balancing right out of the mold. They created dedicated test equipment that could measure dynamic balance while the impeller was actually spinning, providing instant feedback to the operator. The result was faster production and more consistent quality. Even the cooling system was reimagined. Compressing air generates tremendous heat, as much as 205 degrees Celsius, to prevent the fuel from detonating prematurely. The Merlin used a complex intercooler system. 36 gallons of ethylene glycol coolant circulated through the system every minute. Packard redesigned the coolant passages within the supercharger housing, optimizing the shapes for more efficient fluid flow and easier casting. Every single system was analyzed, stripped down and rebuilt for the assembly line, proving that mass production did not mean lowering standards. It meant elevating the process. By August 1941, exactly 11 months after the ink dried on the licensing agreement, the moment of truth arrived. The first V1651, Packard's designation for the Merlin XX, was mounted on a test stand at the East Grand Boulevard plant. It roared to life, hitting every performance benchmark on the first try. When the news reached London, Prime Minister Winston Churchill, a man who carried the weight of the free world on his shoulders, reportedly wept. He knew what the numbers meant. Britain was finally going to get the engines they desperately needed to survive. But making one perfect engine was a science project. Making 55,000 of them was a war effort. Packard transformed their factory into a precision engineering marvel, a veritable arsenal of democracy. The production line for the V1650 utilized dedicated machining centers, a concept that was revolutionary for the time. Instead of general-purpose machines, each station was configured for a specific operation. There were crankshaft machining stations, block-face milling stations, and cylinder-head boring stations. The American mass production philosophy demanded that every operation be repeatable and measurable. If a crankshaft main bearing journal needed to be exactly 2.2495 inches in diameter, the machine was calibrated to produce that dimension and nothing else. It did not produce 2.2492, and it did not produce 2.2498. It produced 2.2495. Exactly right, every time. This eliminated the skilled hand-fitting that Rolls-Royce relied on. A Packard line worker did not need years of apprenticeship under a master craftsman. They needed good training, excellent machinery, and a quality control gauge. Production ramped up ferociously through 1942. By 1943, Packard was producing engines faster than North American Aviation could build airframes to put them in. At peak production, the Detroit plant completed approximately 400 engines per week, double the output of Rolls-Royce's entire British operation. But the real game-changer was the introduction of the V1653, based on the advanced Merlin 63. This was the engine that transformed the P-51B Mustang from a low-altitude interceptor into the allure, war-winning escort fighter the bombers had been praying for. The two-stage supercharger, now mass-produced with Detroit precision, allowed the Mustang to maintain over 200 horsepower at 30,000 feet, the very altitude where the Allison engine had previously choked. The most produced variant, the V1657, powered the iconic P-51D with its bubble canopy. Generating 315 horsepower at sea level, it could pull the Mustang to 437 miles per hour, and sustain combat operations up to 42,000 feet. Suddenly, the tables turned in the skies over Europe. Those engines escorted American B-17s and B-24s all the way from England to Berlin and back. The Luftwaffe pilots, who had previously enjoyed sanctuary at high altitudes, found themselves being hunted by a plane that could outclimb Segelvels, Uvu Minnel dive, Tukt Vincent Minnel to Slive, and outturn them in the thin air. The Germans called the new Mustangs der Amerikanische Raubvogel, the American bird of prey, and they learned to fear the distinctive Clud of Liberation, high-pitched howl of the Merlin engine. By the time production ended in 1945, Packard had built 523 Merlin engines, more than all the Rolls-Royce factories in Britain combined. They had not just copied the British masterpiece, they had multiplied it. The Packard Merlin represents something profound in the history of engineering, something that goes far beyond the sum of its aluminum and steel parts. It proved once and for all that precision and mass production are not opposites. For decades, the prevailing wisdom held that you could have quantity, or you could have quality, but you could not have both. Packard shattered this false dichotomy. They demonstrated that with the right systems, the right tooling, and the right philosophy, you could mass-produce perfection. Rolls-Royce built exceptional engines through craftsmanship. Packard built exceptional engines through systems. Both approaches worked, but only one could scale to meet the voracious demands of total war. The techniques Packard perfected during those frantic months in Detroit, precision investment casting, statistical process control, and the creation of dedicated tooling to ensure consistent quality, became the bedrock of modern aerospace manufacturing. When you board a Boeing or Airbus today, the jet engines powering your flight are manufactured using the spiritual descendants of the principles Packard pioneered in 1941. The legacy of this collaboration echoes in machines we use every day. The bearing technology Packard developed for the Merlin, substituting temperamental copper lead for the robust silver lead indium alloy, revolutionized post-war automotive engineering. Those bearings became the standard for high-performance engines for decades, allowing cars to run faster and longer without failure. Even the headache of the thread compatibility left a mark. Today's international standards, like ISO metric threads, exist largely because engineers learnt the hard lesson of World War II. Incompatible fastener systems create impossible logistics problems. But perhaps the most visceral proof of this engineering triumph can still be seen and heard today. Several Packard Merlins are still flying, more than 80 years after they rolled off the assembly line. The Canadian Warplane Heritage Museum's Lancaster bomber in Hamilton, Ontario, relies on 4 original Packard engines to keep history airborne. At the Renault Air Races, in the unlimited class, highly modified P-51's pushed their Packard Merlins to limits that would have terrified a 1940s engineer. These engines, built to produce 500 horsepower, are tuned to scream at over 800 horsepower, nearly 3 times their original specification. That they hold together under such extreme stress is the ultimate testament to the quality of Detroit's manufacturing. The P-51 Mustang earned its reputation as perhaps the finest fighter aircraft of World War II. But its secret, the reason it could dominate the skies over Europe, was not just the sleek aerodynamics or the courage of the pilots. It was an engine designed in Derby, England, and perfected in Detroit, Michigan. The story of the Packard Merlin is not about American engineering being superior to British engineering, or vice versa. It is a story about complementary strengths. British innovation provided the revolutionary spark. American manufacturing genius provided the fuel to turn that spark into a roaring fire. Next time you see a P-51 Mustang at an airshow, do not just watch it fly. Close your eyes and listen to that distinctive throaty whistle of the supercharger. You are hearing the sound of two industrial philosophies working in perfect harmony. You are hearing the sound of a problem that was solved, not by winning a battle, but by conquering the blueprint. If you found this deep dive into engineering history fascinating, make sure to subscribe to this channel. We are dedicated to uncovering the technical solutions that changed the course of warfare. Next week, we are exploring another invisible war winner, the incredible story of how American engineers broke the Japanese Purple Code by building a mechanical computer from scratch, without ever seeing the actual machine they were trying to replicate. Hit that notification bell so you do not miss it. These are the stories they do not teach in history class, because they are not about who fired the shot, they are about how the weapon was built.